Hello students, let's talk about series parallel circuits and straight line extraction. For this demonstration I'll be talking specifically about supplemental lab number 10. And we have a series parallel circuit here. It's got 7 resistors, so pretty, it's not complex, but it is complicated. So we'll take a look at this, and there's a couple of methods you can use to do this. One of these that's traditionally used is called the resistor equivalent, where you combine series and parallel networks and you go down to reduce it to one single resistance, so you know the total resistance of the circuit, and then you work your way back through the circuit. I'm going to do something similar to that. It's what I've known has been tagged as straight line extraction. It's a little bit different than what I did in school, but I think it simplifies some of the stuff we're doing. So what we're doing is we're taking this circuit up here, and if I were to take these resistors and put them all in a straight line, make them either go all left to right or all up and down, you could do a straight line extraction like that. So that's simply what we've done here. And I've taken out the power supply, just labeled it positive and negative. Sometimes the bottom part of this, or the negative in the power supply, is the common ground, and it's labeled that way also. So what I've done is I've taken these 7 resistors and I've drawn them into this circuit, and I've just simply labeled them as R1, R2, R3, and drawn the schematic symbol. But for simplicity's sake, what we're going to do is we're going to get rid of that schematic symbol, and we're going to replace it with the ohmic value. And we're just going to use the numbers. I'm not using the ohm signs, the omega sign, or anything on this. And I've taken from this circuit here showing the power supply, I've drawn a straight line with the resistors, and now I'm going to simply show this circuit as just the ohmic values here. And so what we're going to go through here is we're going to combine what is in series and add them up, and then we're going to use the product over the sum or the reciprocal formula to calculate parallel networks and reduce it down to single resistance. So this is page 1, and now let's go back to page 2. We're going to look at 2, and I've just redrawn what was on page 1. And using what we know about series and parallel circuits, we're going to apply those principles to find the total resistance. So the first thing we're going to do is add this 680 ohm and 1000 ohm resistor. We're going to add that up here. And you see down here on our screen that 1680, we've just added those 2 resistors that were in series. So we redraw and reduce so we can further analyze this circuit. So that's what we've done. The next step is now we're going to look at this 1680 in parallel with the 560, and we're going to figure out the resistor equivalent to there. So we can either use the reciprocal formula, or we can use a product over the sum if it's just 2 resistors. And so I've done it both ways, just showing it here, and we come up with 420 doing that both ways. Now what I've done is I've redrawn this circuit again, and now you see we reduced it from 7 resistors to 5 resistors here, and these are resistor equivalents. These are theoretical resistances, and so I've drawn it here. And so what we're going to do is, you see that one branch is in series and the other branch is in series. We're simply going to add those numbers together. So that's your 600 and 890, and those are in parallel. So to calculate that resistance, we're going to use the product over the sum process again. You see that R and the EQ there, that just resistor equivalent is all that means. So the resistor equivalent of this parallel network is 358 degrees. I combine that with that R1, which is 150 ohms. I add those together, and now this is your total resistance for the entire circuit. So we've gone through that whole process, and we found out one thing about the circuit. We found out the total resistance. So the process now is, what we would do is that we would look at going backwards and start applying our voltage and calculating currents, and start applying current and calculating voltage depending on where we are in that circuit. So that's what we're doing here. So we're going to apply 6 volts. I've chosen a different voltage from what is actually in Supplemental Lab 10. And so we're just going to pick 6 volts, and I'm working my way backwards through this circuit now. So if I take 6 volts and I divide it by 508.39 ohms, I get a current of 11.8 milliamps. That's my total current. That's the current that goes through the whole circuit. And in this circuit, there's only one resistor that's in series with the whole rest of the circuit, and that's R1. So this 11.8 milliamps goes through R1. And then we start calculating our voltage drop. So I take it 11.8 milliamps, multiply it by 500 or 150 ohms, and get my voltage drop for R1, and then the rest of the drop on the rest of the circuit. And then I work my way backwards through that straight line extraction, calculating voltage drops and current, just applying Ohm's law. And so we go through this whole process. We go there, and then we sort of start drawing the circuit back through there, calculating my voltage drops in my circuit. And I've gone through all this stuff, and we have one final step here, and that's going to be page 5. And what I've done with page 5 is I've sort of made this a little bit larger. I've drawn out the current and voltages everywhere. I've filled out a volts, amps, ohm chart here, sometimes called a Verpi chart. We could simply use Watt's law if we want to calculate the power in this case. And this is how you go through a straight line extraction. I hope this helped you understand this process. We'll get some more practice in here in applying these principles. And I hope this video finds you in good health.